Welcome to the iPhone webinar. It's time flies. I see this webinar starts from I think last year, 2020 June, due to the COVID-19 pandemic. So President Aaron and our decided to start some virtual study platform for our medical physicists in the iPhone arrows. So now today has been our 12th webinars, almost 1 year exactly. So now today we are lucky to have a talk from Seoul. Is Dr. Chung and our moderator, Dr. Supriyanto Ardjo, and the topic today is the gamma knife, the physics, basic physics part. So I will give a brief introduction of our moderator, Dr. Supriyanto, and then he will control the whole meeting. Dr. Supriyanto Ardjo Pawiro, he got his PhD from the Center for Medical Physics and Bioengineering in the Medical University of Vienna, Australia. He has been working. He's working as a teaching and research in the Department of Physics in the University of Indonesia. As we can see, he has actually fruitful experience in the medical physics field. He has been in the clinical medical physics training program in the Singapore National Cancer Center of Singapore. Also, as the adjunct medical physics in the Department of Radiosurgery in Jakarta. Also, he got his PhD from the Center for Medical Physics and Bioengineering in Medical University of Vienna. So this is show you some of the basic idea about this webinar. This webinar will be sponsored by the Continuous Progress Development Points. So you will, after the meeting of the webinar, you need to register for the points, CBT points, but we have double check as you need to listen at least 40 minutes or sometimes, then you will get the certificate. So now this is the basic idea of the webinar. I will hand this to Dr. Supriyanto Pawiro, please.
Thank you very much. Thank you very much, Dr. Junios, for the introduction. As introduced by Dr. Jin, that we have the 12th webinar of EVOM today with the title of Basic Principle, Dose Planning, Advantage, and Quality Assurance of Gamma Knife Radiosurgery. As we know that in gamma knife, the medical physics will involve in the radiotherapy, in dosimetry, and also in planning. So in this webinar, Professor Chung will describe more detail about the implementation of the IEA technique report series for 483 on absolute dosimetry, and also we'll talk more about the end-to-end test to evaluate the accuracy of the system. Before Professor Chung delivers the lecture, I will show you this curriculum vitae that Dr. Chung, Professor Chung, graduated from the doctoral degree in experimental physics in 95 from Seoul National University, and then doing postdoctoral research at Korean Atomic Energy Research Institute. Dr. Chung started working at the Department of Neurosurgery, Seoul National University College of Medicine in Korea in 1997 and became full professor 2014. Currently, he is the chair of the International Relations section in the Korean Medical Physics Society. He also very active in Korean Medical Physics Society and also in Korean Radiosurgery Society. He published many publications in peer-reviewed journals, seminar, and also delivering lecture in many medical physics and radiosurgery event. Before the Professor Chung delivered the lecture, for participant, if you have the question, please send it in the chat box, and we'll discuss in the discussion session. And now, please, Professor Chung, please deliver the lecture about 45 minutes. Time is yours.
Thank you. Okay, let me share my presentation first. Now you can see my presentation. Yes. Thank you, Mr. Chairman, and I'd like to thank you everyone for coming to my webinar. And I try to do my best so that you can enjoy my webinar. So as you can see, I changed my title. Actually, it's simplified very much, but the contents will not be different. So first, I will talk about the general facts about gamma knife, the beginning, goal, principle, and the difference between radiosurgery and radiotherapy. Then my main topic will be verification of gamma knife radiation. So I'll start with measurement of absolute dose rate and calculation of helmet out factor and verification of dose distributions of gamma knife. Then I hope I can have time to talk about the accuracy of frameless gamma knife surgery. So in order to understand the beginning of stereotactic radiosurgery, we need to see the situations of neurosurgery early 20th century. At that time, the mortality rate after neurosurgery was nearly 40%, about 0.5% usually. So this 40% was with the best hands like Harvey Cushing and Oliver Corona. The other neurosurgeons' output was even worse. But even with this high mortality, they kept opening the skull because the patient would die without this neurosurgery. So their act was saving the patient, saving about half of the patient rather than killing half patient. But the situation was different for functional neurosurgery patient. Functional neurosurgery disease patients like trigeminal neuralgia and Parkinson's disease, because they wouldn't die even without any patient. So they wanted to cure those functional patients without opening the skull. But the question was how? So they decided to use radiation, but because they did not open the skull, they need a stereotactic technology to approach their target. So when they combined the radiation with stereotactic technology, it became stereotactic radiosurgery. So their goal was to destroy a lesion in the brain, not treat the tumor at the first time. So the first and early applications of stereotactic radiosurgery was functional disease patients. And in 1951, Dr. Lars Lexer of Lund University, at that time Karolinska University, he published a very important paper, the first paper on radiosurgery. It is so-called Citation Classic. And in that paper, he accredited to Kurt Liden, who was the physicist at Lund University. Actually, he did many things on gamma knife, you will see. And in this paper, there was no experiment, no data, only concept was described. Those all good days. We could publish the paper without any data. Anyway, in the paper, he defined the radiosurgery as delivery of a single high dose of radiation to a small and critically located intracranial volume by focusing the radiation. So the first trial was like this. They used the stereotactic arc and put an X-ray tube over 280 kilovolt tube, like this. So it's like the same principle with conventional line-up entry. So this was before the line-up. But soon he gave up this method because this X-ray energy was not so high enough to pass through the skulls. Anyway, the principle itself was to focus radiation to a single point. That's the difference between the radiotherapy and radiosurgery. We all know that when you try to a region, this black one in the brain with the external radiation, we give radiation like this. Then the normal brains between the skull and between the skin and target receives more radiation, and the volume of the normal brain is much larger than the target itself. But even with this, poor conditions, we can expect therapeutic effects because we give the radiation in fractionation. So we use the benefit of the so-called 4R. That's conventional radiotherapy. So because we use fractionation, this approach is good for high alpha-beta ratio tumors like cancers and glioblastomas. But the situation is different in radiosurgery. In radiosurgery, we focus the radiation to a target only, so the radiate normal volume is much less than target volume. And we give the radiation in a single session. It means we don't use the 4R. So the indication of radiosurgery is different from radiotherapy indications. The high alpha-beta ratio tumors like cancers and glioblastomas, we cannot give much, enough radiation in a single session because they require too much radiation. But for benign tumors like, vestibular and meningiomas, we can give enough radiation to hold their growth, not kill all of them. So the main indication of radiosurgery is now benign tumors and arteriovenous malformations and sometimes functional disease. And brain metastasis is one of the main indications. It's a little different story. So now let's focus on radiosurgery. We want to kill everything inside our target, and we want to save everything outside. In order to approach this goal, we need to very high accuracy to locate the target and focus the radiation. Also, the radiation should be as steep as possible. This infinite slope is ideal, but we know that it's not possible in the real world. In the real world, we use many different approaches to focus the beam. It's the difference between the device to device. In case of gamma knife and the cyber knife 2, we use multiply directed beams. So in gamma knife 2, around 200 different direction beams are focused at a single point. Each single beam is weak enough not to destroy the normal brain, but at the center, the intensity becomes about 200 times higher, stronger, so we can expect therapeutic effect. This is the principle of gamma knife, very simple. With this simple principle, in 1963, Leiden and Björn Larsen applied a project to Swedish government. They called that device strap-kniven, in English, radiation beam knife, which uses cross-firing cobalt-60 beams. And the Swedish government required monumental amounts of huge amount of documentation, and the result was naturally rejected. That's what happened every time for our project. But fortunately, Dr. Lars Lexer has different power. His daughter married to Bo Axel Jones' son, and this Axel Jones group owned Motala Parkstad. It's one of the largest shipyards in the world at that time. So they built the first gamma knife unit in the shipyard, Motala Parkstad. And the first gamma unit was like this. They put cobalt sources around the semi-spherical helmet. So these beams, at the time, there was 179 different beams and was focused at the point. And soon after, they changed their structure. I don't know how do I call it. They cut the top part and I can say semi-hemispherical shape. So we call it helmet. So there are primary collimators here. Cobalt doses are over this primary collimator, and this helmet worked as a secondary collimator. So we fix the patient head here with the frame usually, and when we start the treatment, the patient, this couch moves in, and the primary collimator and secondary collimator matches each other, and the radiation starts. After the radiation finishes, the couch moved out, and we remove the frame, and patient go home. It's very simple procedure. This is model C. The recent model, Perfection and Icon, they put some covers here, and the helmet is embedded inside the main body, so we cannot see any holes these days. So gamma knife had evolved several times. The prototype was 1968, and the model U was installed in the United States, model B soon, and 1999, model C, then 2006, Perfection. With Perfection, the procedure was fully automated. So we just push a button, then the machine takes care of everything until the end of irradiation. It's very good for me. And 2015, the newest model Icon was introduced to the market. The Icon has a compensity here because they share the same irradiation unit. The physics about radiation given in this presentation can be applied both for Perfection and Icon. Okay, let me start with the traditional way of gamma knife surgery. It's a frame-based gamma knife surgery in single session. In the early morning, 7 p.m. usually, the patient comes to gamma knife center, and we fix the patient frame with 4 screws and take stereotactic image. Then patient take rest. During that time, the treatment team make a treatment plan. After the planning is finished, we go together to the machine and irradiation, and the patient go home after removing the frame. It's a one-day procedure. It's very simple. It's very convenient for the patient. So in order to check the accuracy of frame-based GKS, we need to see the image-related factors, radiation-related factors, and finally, we need to perform overall accuracy measurement. In this presentation, I will not handle about the image-related factors and focus on radiation-related factors and overall accuracy measurement. The first thing is to measure the absolute value of observed dose rate water over gamma knife. The phantom is a solid water spherical phantom. Its radius is 8 centimeters. And ion chamber, we have 3 types of ion chambers, and electrometer and thermometer and barometer. We have standard laboratory level devices, and measuring the dose rate of gamma knife several times means we are measuring the half-life of cobalt-60. So when I calculate the half-life, it was 5.27 years. It's very close to the known value. So we can say at least our system works fine without any systematical problem. But the question is the absolute value itself is accurate or not. Because this is a small field dosimetry, we need to see the TRS-483, which was published in 2017 November. They give a code of practice for reference and relative dosimetry of small static fields. They suggested to use machine-specific reference field for each device, and that MSR field should be close as possible to 10 by 10 square centimeter field. And this is the formula they recommended in order to know the dose to water at a single point. We measure a charge with a detector, and this NDW value is given from the SSDL, and there's a factor to correct the small field related factors. And they call it beam quality factor, beam quality correction factor. But we know that this is not beam quality correction factor. The only thing this factor can be beam quality factor is it is located at the same position with the formula of TRS39A. So I think it's better to call it MSR correction factor. And let's see what they describe about the gamma knife. They suggested to use equation 25 like this. I just showed you. But you need to be very careful to apply this formula with a gamma knife. There's a sentence. Note, however, that as reference dosimetry in gamma knife beams is usually performed in plastic phantoms, the correction factors include conversion to observe dose to water. It took more than a day, several days to understand the meaning of this. So let me repeat. This is the formula for line up in using water phantom. We saw it twice already. And because we use plastic phantoms in gamma knife, they suggested to use this formula for plastic phantom. The reference of measurement is done in plastic, and we need another correction factor, phantom correction factor. But for gamma knife, they suggested to use this formula, which is validate for water phantom. So when you see this formula for gamma knife, you have to understand, you have to look like this. The measurement depth is 8 centimeter water, but the plastic phantom radius is also 8 centimeter, not equivalent depths. And these factors are combined into this one factor. Even though they use the same notation for this and this, the meaning is different. So it's very confusing. But once you knew this fact, it's easy, but the first time it's difficult to understand. So let me explain in more detail. When you send your ion chamber to an SSDL to calibrate, they use this setup. There's cobalt-6 source. The field size is 10 by 10, and the SSD is 100 centimeter. Depth is 5 grams per square centimeter. And they give this correction factor, conversion factor actually. This NDW is a factor to convert measured charge to observe dose to a point in the SSDL. When the chamber is returned to your hospital, you can reproduce every conditions just like the SSDL, except the source. Now the source is line up, which is different from cobalt. So in order to obtain the dose to water, we need another factor. It considers the difference between the line arc and cobalt source. So this is the beam quality correction factor. So you know this formula very well. But for small field situation, the beam shape, field size, depth, SAD can be different. Gamma knife, all of these factors are not same with reference field. So in addition to beam quality correction factor, we need another factor considering these differences. Let's call it small field correction factor for the time being. And for gamma knife, it is even more complicated because we use plastic phantom in the spherical shape. So we need another correction factor, and let's call it phantom correction factor. So we have three conversion factor, correction factors now, because it is too complicated. They combine these factors into one, and they use the same notation. So please don't be confused. So this is the MSR correction factor for gamma knife, which was given in TRS 483 and in many other papers. So now understand how to do that. So let's try to measure the dose rate. And this is the reference conditions given in TRS 483. The phantom materials, water or plastic, usually plastic. And phantom shape and size is hemispherical at top and 16 centimeter diameter. And measurement depth, jet reference 8 centimeter. No, this 8 centimeter is water and this 8 centimeter is plastic. So it's very confusing. This note B says polystyrene is 8 centimeter, PMA is 7 centimeter, but every data is given with 8 centimeter until now. And so they suggest to put the chamber at the center of the machine. It looks okay, but they did not specify the chamber orientation. We can put the chamber along the couch direction, jet direction, and sometimes we can put the detector perpendicular to the jet direction, but there is no specification on orientation. You will see what is different. And they specified SSD is 32 centimeter, but this, you know that this is wrong because the perfection, the sources are distributed on a conical surface and the phantom is sphere. So no, not a single distance can be defined. So it's meaningless to talk about SSD with perfection. And they also said field size 1.6 or 1.8 centimeter, it means 60 millimeter collimator or 80 millimeter collimator, but those are just a name of the collimator, not the field size. The gamma people know that the field size of 60 millimeter collimator is about 22 millimeter. Polycell half mass. So this one also needs to be updated, revised to the correct values. Anyway, they give the MSR correction factor for this formula, and I think this is good for solid water for the factors. So those factors were obtained by Monte Carlo simulation, and for ABS phantom we have to see. We'll see later. So we can calculate this MSR correction factor by Monte Carlo simulation. This is the SSDL formula. This is our MSR field formula. So K factor is just simply the ratio of this. It's not difficult. But in order to do this with Monte Carlo simulation, we need an assumption. Let's say in the standard laboratory, the measured charge and those has related with N detector 0. And in the MSR field, M and D is related N detector MSR. Our assumption is these two coefficients is the same. It is very natural. The observed dose to the detector and output charge from the detector is always proportional. And this assumption is to say that that proportional coefficient is constant. It should be. That's the detector characteristic. Otherwise, we cannot say it is a detector. So this is a very natural assumption. So with this assumption, we can say this MSR correction factor becomes this. We can replace the measured charge with Monte Carlo simulated observed dose to the detector. The meaning of this MSR correction factor is this. There is a relation between the observed dose to detector and observed dose to a point in water phantom. And this MSR correction factor is the ratio of that relation in the MSR field and standard laboratory field. It's simple. the relation between the observed dose detector and observed water can be different between condition to conditions. So we need to calculate it. So, and some people did. They got information of gamma knife from Electa and different simulation codes. And this is a beautiful picture from JAWS. And you can see we can put the detector along the Z direction, and we can put the detector in the XY plane, which is perpendicular to the Z direction. We do it only for ABS phantom. And this is the beautiful figures from Shah-Smith paper for the chambers. And this is the result. It looks very complicated, but I want to emphasize only two things here. With the solid water phantom, the PTW 31010 and 31016, the correction factor, the correction is very small. It's less than 1%, which is much less than my first guess. So, I know some people do not apply this MSL correction factor. It will not change much, the result. And the second one is ABS phantom. The JAWS result and other results are different because JAWS put the detector in the XY plane and others put the detector along the Z direction. So TRS-4HC must specify the chamber orientation in their code of practice. Okay, we just finished the absolute dosimetry, and it's time to see the relative dosimetry. It's a so-called collimator out factors. We know that perfection has 4 different sizes of collimators, 4, 8, 16. When you measure the dose rate inside this solid water phantom, the absolute dose value at the center is different for each collimator. Dose of 4 is smaller than D8, and it is also smaller than D16. So the ratio of the D4 to D16, D8 to D16 is collimator out factor, sometimes called helmet out factor, and sometimes field output factor. The same meaning. So let's say omega 416 is collimator out factor of the 4mm collimator. Then LGP, the treatment planning program of gamma knife surgery, uses omega 416 of 0.814, and omega 816 is 0.900. So it's our task to check how accurate these values are. We are medical physicists, so we need to check the accuracy. Before you go further, let me clarify the symbols. It's very complicated, so I will use this symbol, the quantity, and the superscript is the collimator size, and the first subscript is the observer material, and second subscript is the phantom material, and the things between the parentheses is observer volume. So for example, DWW40 means it's observed dose to water, and the water is a point at the center, and the phantom is water also, and the collimator is 4mm. M for detector, solid water detector means measured value by a detector, and the material is also detector, and the phantom is solid water, and the field is 4mm. Detector 4, D4 detector, W detector is observed detector in a water phantom. Okay, this is solid water phantom, this is water phantom. And D4 WW detector is observed to water, but the shape is not the point now. The shape is the same as the shape of a detector. But the detector is formed with water in this case, and the phantom is water. So we have 4 factors to consider for each quantity. Now, the output correction factor, we need to think about the output correction factor. The output factor omega 416 is the ratio of these two doses. And in order to have this, we need to measure the dose rate. But we cannot use this measured, the ratio of measured values directly, because we know that we need a correction factor for small fields. And this correction factor is called output correction factor between 4 and 60 millimeter. And this definition is just like the MSR correction factor. It is the ratio of the ratio, those two point water and measured quantity. Under the same assumption, the measured quantity is always proportional to observe those two detectors with same proportional coefficient. We can use this formula to calculate output correction factor. So in this case, the meaning of output correction factor is like this. There is a relation between the observed dose detector in solid water, because this is gamma knife, and it is converted to dose to point water in water phantom. This relation can be different in 4 millimeter and 60 millimeter. This difference is the output correction factor. And TRS-483 presented the output correction factor. Actually, this is the exactly same result of Ben-Mark-Laub study published in 2015. And you can see we need maybe 4 to 5% differences. And this is the graphical result. So this left part is the previous, before 2011, and this factor, this 2011, 2013, there's some, no plastic scintillator yet, and these 5 are actually the same, because Ben-Mark-Laub applied their devices to 4 different gamma knives. So 8.8 millimeter, it looks okay, but for 4 millimeter, maybe we need some more calculation. So TRS-483, we can go further. 483 suggested to use a detector which is perturbation-free except volume averaging, if it is possible. It means we need to use some detector material which density is very similar to water, not like diamond, not like diode. So the plastic scintillator will be, a candidate. So for every detector, we can change this value to this. This simple cancellation of the numerator and denominator. And this D4WW can be written again like this. So in order to have D4WW0, in order to have the observed dose rate to point water in water phantom, we need to calculate observed dose to detector in solid water phantom with finite volume. Then this is a correction factor which takes into account the perturbation by solid water phantom and detector material. Both of them are not water, so there must be some perturbation. And the last part is the volume averaging factor. The numerator is the dose water at the center point. And the denominator is dose to water of the detector volume. So this is volume averaging factor. If this perturbation factor is 1, and if we can calculate those averaging factor, we can have this output factor exactly. Let's see. So we made a very interesting detector, isodose shaped scintillator. The material is plastic scintillator. Its density is close to 1, and the shape is the same as some of the dose isodose surface. For example, here, the dose distribution is given in voxels, and this center voxel is the dose to the center point. If we make our detector in this shape, then we know the dose rate to every voxels inside by the gamma knife LGP. So we can calculate the volume average factor easily. So we made the scintillators, two types of scintillators, 97.2 and 95.6%. So it was made by 3D printing. And we can easily calculate the volume average factor. It's a simple, simple numeric. We don't need any integration, just summation. And this is the value. This is the K416 of the 97.2% to 1.018. And those was used from LGP. And to be sure, we performed our own Monte Carlo simulation and we got similar results. And the perturbation factor is this. Let me show a much easier way. So for each field, this perturbation factor means the ratio of observed dose to the water in the shape of detector, and denominator is observed dose to detector in the solid water phantom. There is a relation connecting these two values, and the ratio of this relation in the 4 millimeter and 60 millimeter is the perturbation factor. So we are doing the Monte Carlo simulations. Preliminary result is P416 is 0.996, very close to 1. So we can measure the output factor of gamma knife. So with ISS is here, we have a cover and optical fiber is connected to photomultiplier tuber, and this power supply and temperature is automatically self-controlled, and we measure the current from the PMT. And this is probe adapter without ISS. We applied a reflector and we put ISS here, and reflect again. We cover the ISS with cap. And before we do anything, you can see the optical fibers here. And this is the dose distribution around the ISS, or ISS1 and ISS2. So when we measured the output factor, this is a preliminary result yet. For this 97.2%, K416 was 1.018 and P416 was 0.996, and measured output factor was 0.902 and 0.818. Surprisingly, it was very close to the LGP values. So we are still, no, it was too close, much better than our expectations. So we are reviewing our processes if we did anything wrong. So soon we will publish our data. Now it's time to see the relative dose distribution. Usually we check the single shot dose distribution with a film, EBT3 film, and we just check the one-dimensional dose distribution. But we have a film, then why not gamma index pass rate? When we did gamma index pass rate check, it is very good, more than 99% pass rate with 1 millimeter, 3% standard. But this is just a single shot distribution. We need to check the multiple shot dose distribution in an anthropomorphic phantom rather than spherical phantom. And not only at the center, but different locations. So we did this at 5 locations. So process this. We set a film, actually dummy film at this time, and CT scan, make a plan, and erase the real film, and get the measured dose distribution. And we have calculate dose distribution and compare. This is the same. And this is the plan we used. And we used 47 films for the single shot plan and 46 films for multiple shot, 47 and 46. And from the single shot, we could find the accuracy in position was 0.6 millimeter, and the standard deviation is not small. And from the multiple shot, the gamma index pass rate is about 99%. It's very good. So let me summarize first. The MSR correction factor for perfection was not much different from 1, at least for PTW31010 in solid water phantom. It was good for me. And irradiation with gamma knife could be performed with errors less than 1 millimeter using phantom CT images. MR images will have bigger errors. And gamma index pass rate with multiple shot plans were higher than 98% with 1 millimeter 3% error range. Let's move to the gamma knife icon. So icon has the cone beam sheet. The radiation part is same as perfection, and it has a cone beam CT. It has a patient monitoring system. So by combining this, we can perform frameless gamma knife surgery with gamma knife icon. This is a typical procedure. We have non-stereoscopic MR images, and we take the reference cone beam CT, then register these two images. Then we have stereotactic coordinates for the MR images, so we can make treatment plan. After finish the treatment plan, we take the patient to the machine and take another cone beam CT. So during this reference, and patient moved, so we need to register again. If we found any movement, the LGP automatically, convert the coordinates of the shots, and we can start the treatment. And during the treatment, we can check the patient motion with high definition motion measurement system. And after finish, the patient can go home. So for the frameless gamma knife surgery, we can easily assume that there must be some additional errors related with, cone beam CTs. So we'll see. First thing, we want to see the accuracy of correlation between MR images and cone beam CT images, which gives the stereotactic coordinate values to non-stereotactic MR images. But it's okay. So for this whole procedure, first thing is we will see this part, correlation with the MR images and reference cone beam CT images. But this, we know that MR images have distortions, so I'd like to do it with CT images before I use the MR images. So I took the stereotactic images, CT images first, then we can define the coordinate system using these fiducial markers. So we have fiducial marker-based coordinate system here. Then I took cone beam CT images. Then it has its own coordinate system. It is cone beam CT-based coordinate system. Before I do anything, I compare these two systems. I found there is about 0.5 millimeter difference. The question is which one is correct. I skipped, I took out several slides, but I checked this cone beam CT-based system is much better. So I used this cone beam CT-based system as a reference. So, to check the accuracy of correlation, I correlated these CT images to cone beam CT images. Now, these CT images have another correlated coordinate system. So I compared this correlated coordinate system to cone beam CT-based coordinate system. And to compare the locations, I need some landmarks. So I found some air bubbles in the phantom, 15 air bubbles like this. And you can see cone beam CT and CT, there is clearly some differences. Of course, this is the worst case. And this is the result. Upper 3 is the one-dimensional display from delta X, delta Y, delta Z. And lower 3 is the three-dimensional differences. Before I do anything, there was 0.5 millimeter differences. After I corrected without movement, the phantom was fixed at the same position. The difference was reduced. But when I move the phantom in an arbitrary way, very unrealistically large movement, then the difference became the same with the fiducial markers. So at least for phantoms with the CT images, we can have the same accuracy with correlated images. Now it's time to check the cone-beam CT to cone-beam CT co-registration. It's easier than before. Now we have a reference cone-beam CT. We move the phantom and take cone-beam CT and co-register, and this image is now co-registered position. So this and this should be the same because it is the same point. So before co-registration 0.12, no movement, rotation only, arbitrary movement 0.2 millimeter difference in 3-dimensional. So I can say it is very accurate, at least with phantom and CT images. So it's time to do end-to-end test of frameless case. So I repeated all actual procedures with phantom 3 times, and the result was 0.5. Still, the aviation, large standard deviation. Anyway, the mean value is only 0.5 millimeter. So it is similar to the accuracy of frame-based gamma knife surgery, at least with CT and phantom. Now we know that gamma knife surgery is performed with MR images, which has geometrical distortions. So I purchased another phantom, which I can get MR images. I repeated the same procedure, and this is the result. CT, I got the similar result, 0.2 millimeter differences, but for MR, fiducial marker-based system showed about 1 millimeter difference. It's typical. We know that our many previous studies reported similar values, but the coordinate stem showed only 0.4 millimeter difference, and there was a statistically difference. So I personally believe it's better to use co-registered method. It is even better because we can get MR images without the frame. The frame itself generates, severe amount of, distortion, especially the lower regions, which is close to the frame base. So let me summarize. The accuracy of gamma knife, of the frameless gamma knife, interfraction phantom setup for frameless gamma knife could be produced with 0.2 millimeter accuracy. And frameless gamma knife surgery could be performed with similar accuracy to frame-based gamma knife surgery. It is not inferior. It's my belief, personal belief. But we should always remember that for frameless gamma knife surgery, the patient can move during irradiation. It's out of our control, out of our control. Even if we use the very tight, mask, the patient can still move up to 1 millimeter or so. So we must remember that do not forget the patient move during the frameless gamma knife surgery. Thank you for your attention, and I really hope you can meet in the end of December in Bangladesh. Thank you.
Okay, thank you very much, Professor Chung, for a very good presentation. And we still have time to have the question from the audience. Please set your question in the chat box. Is there any question from the floor? Okay, I will start with my question. Thank you very much for the presentation. I will ask for the MR and the CBCT registration. Use the phantom, right, for the MR, from the MR. What is the concentration of the like for the liquid they use from this scanning?
I'm sorry, I cannot answer because I just purchased from the company, and it's their secret. They don't release the information.
Okay.
I see. Yeah.
Okay. Thank you very much.
Yeah.
Is there any question from the floor? Okay.
By the time,
yes, please.
How many gamma knives do you have in South Korea? And with the cyber knife, chromotherapy, and other the linear accelerator X knife, what do you think still, how much scope for the gamma knife units and the gamma knife treatments?
Okay. The first question is easy to answer. We have 21 gamma knives operated in 20 sites. Samsung Medical Center, Samsung Hospital, they are rich, so they have 2 gamma knives. And about, I don't remember exactly because we don't these days, but around 10 to 15 cyber knives and around 15 to 20 tomotherapy. And as we don't have X knife these days, so the people use radiation dedicated machines. And what was your last question? I forgot, I'm sorry.
No, if we have the cyber knife, tomotherapy, or X knife, still we can do the SRS and SRT. So what added advantage we have with a gamma knife?
You mean the advantage of gamma knife?
Yeah, what is the added advantage of gamma knife?
It's very difficult to say. I think the physical characteristics of radiosurgery machines are similar these days. I don't think there is any, superior system. But there is some political issue between neurosurgery and radiosurgery department, radiation therapy department. So the gamma knife, all of the gamma knife in Korea belongs to neurosurgery department.
Yeah, across the world.
Yes. So it's a political issue.
Okay. There's one question from Fahime that the question is, what is the indication of gamma knife overall, which tumor, and in this what is comparison with the SRS?
Yes, I can see the question here. Gamma knife is one form of SRS, but the gamma knife can be used only for cranial lesions. So we cannot apply so we can use gamma knife for regions located around the foramen of Monro in means C1 or C2 level. But if the tumor is located under the C2, we cannot use gamma knife. Yeah, because the tumor can move. So we fix the skull. Even if we fix the skull, the tumor can move when it is located in the cervical spine.
Okay, thank you. And there's one question from Kazuo, that how much is the margin set for the famous?
Yeah, it is also a difficult question. It depends on people, but I will tell my opinion. I don't, claim that my opinion is correct. But the important thing is all the data accumulated until now on gamma knife was obtained without any margin. So those volume relation, when the tumor volume is 10 cc, we give 12 gray. When the tumor volume is 12 cc, we give 9.5 gray. And that kind of relation was obtained with data without any margin. So if we give some margin, how do we determine the dose? It's a very difficult problem. So we don't set the margin, but if the patient, people will start the treatment with mask treatment, premise treatment, we can, predict a little bit. Or when you see the patient, she or she is not so cooperative, we can expect he or she would move in that case, we keep a little margin, maybe 0.5 millimeter or so. But in other cases, we don't keep any margin, and we try to keep the patient not move during the radiation. Yeah, that's our policy, but it's just our policy. It's not the fixed answer. Yeah.
Okay, thank you very much. Okay, Professor Arun, do you want to give some question? You still mute.
Yeah. During one of the AOCMP meetings, I have heard to one of the talk where China has developed the gamma knife, which can oscillate and treat not only the cranial, but the body parts everywhere. May I know what is the status of that thing? Because that time it was to come into the market.
Yes, I'm also very curious about it. They give presentations. I know the developer Song Shipeng. He is a kind of great guy, very genius. He developed many different types of gamma knives, but I don't see any actual sites. I've never heard of any site which uses it. So I'm sorry, I cannot give any information. I myself am very curious. I want to know about this situation.
Yeah, me too. Actually, we are thinking why they developed the subknife for the body. Yeah, we know it's when we talk about SRs, it should be precise. It should be the tumor should be not movable, like. But for body, yeah, I think they are customizing. Oh, they are doing some commercializing things, but not too many centers accept the gamma knife for the body. I think it's more basically they are selling the idea. I'm not sure the results yet. Thank you. Yeah, it's very wonderful talk. Any more questions? Oh,
I think no question. So I think we can come to the end of the session.
Yes. Okay. Thank you.
Okay. Thank you very much, Professor Chung. Also, all participants involved in the discussion. So we come to the end of the session, and thank you very much.
I will take over here.
Give back to the Jin, please.
Yes.
Goodbye.
Okay.
Just wait.
Yeah.
We are not closing.
Yes, thank you, Dr. Chen and Dr. Supriyanto. Yes, thank you very much for the wonderful talk this afternoon. I actually learned a lot about the subknife. Actually, this is really a wonderful and useful talk. I hope we will have you back in our future webinars too. Okay, and Dr. Aaron is planning some big idea about the summer school, something like virtual school. So hope someday we will invite you back for our lectures. So thank you. Yeah, really.
Thank you.
So at the end of this webinar, we are just want to emphasize that the CVD points was through the registration, but the final approval was not relied on the registration only. So we will also check the time you spend on the webinars. Sometimes, some people will come late and spend only 10 minutes. We don't think that this is good, enough time for you to get approval for the CPT points. So this is the register link actually. Yeah, you can register, but don't spread it. Yeah, sure, don't spread it. We will check it now, and we will check the time that the people in the meeting too. Also, announce for the next webinar will be the next one is June 3rd. It's a talk from China, Zhang Yibao. He will talk about something knowledge-based planning, and our moderator will be Mary Zhong. Is right, Dr. Aaron? This is right.
Yeah.
Okay. Also, we have already scheduled our webinar schedule for the next half year. Let's see. This is the some of the list of the talkers and the moderators. So we will beginning every month, out to finish one webinar, we will release these lists. Okay, so I think this comes to the end of this webinar. Do you want to say more, or no? We will close this webinar.
Thank you.
Thank you. Okay.
Thank you.
No,
Thank you, everyone.
Good evening.
Bye.
Bye.
Thank you.